Hello, welcome to 100C. So in this course, we will continue studying field extensions, which were initially started to understand zeros of single variable polynomials. After we are more or less done with this subject, we try to understand zeros of multivariable polynomials, and we start with linear polynomials. That would lead us to a concept that's called module theory, because we want to understand zeros of linear polynomials, a system of linear polynomials, not only over a field, but also over a ring. After briefly we study module theory, especially modules over a PID, we will study zeros of multivariable polynomials over a field. But first things first, let's review what we have learned about fields so far in 100B. So far we have learned about splitting fields. So what does that mean? We started with a single variable polynomial, and then we showed that we can find an extension of our base field where this extension contains all the zeros of this polynomial f. And we can consider the subfield that is generated by these zeros. That field is called a splitting field of the polynomial small f over the base field capital F. So we showed the existence of such a field, and that we call splitting field of the polynomial f over the base field capital F. And again, it means that I can find elements alpha 1, alpha 2, alpha n inside this field E, and write down the polynomial f as product of these degree 1 factors, which means I can find all these zeros inside this larger field. And this larger field is generated by the base field capital F and these zeros of the polynomial small f. Then what we did, in order to understand field extensions, we viewed them as vector spaces. We extended the concept of linear spaces, vector spaces. You have seen these concepts over real numbers or complex numbers. And then we saw that we can extend those definitions and work with vector spaces over an arbitrary field. And this was particularly important when we wanted to understand a ring A that contains a subfield F. So that way we can view this ring A as a vector space over the field F. In particular, the dimension of this ring can tell us something about the structure of the ring. We use this for field extensions. And we called a field extension a finite field extension if the dimension of this extension field is finite over the base field capital F. Okay, so let's go through the notes as well. So if I tell you that E is an extension field of the field F, sometimes I refer to this smaller field as the base field, then we can view E as a vector space over the base field F, and the dimension of this vector space over F is denoted by the same notation as we used for index of subgroups, so E 2 dots F. We had proved the Tower formula, the Tower rule for field extensions. But I'm using this notion of field extension again and again. Let's make it formal. What do I mean by that? So whenever I have an extension field, so if E is an extension field of the base field F, sometimes we want to capture both E and F in the same phrase, and that pair of fields is called a field extension. So A field extension then, from this point on, is the pair of E and F, where E is an extension field of F, where F is a subfield of E. And we denote it by this admittedly a bit confusing notation, E over F. So in field theory, from the context, you should be able to say that E over F means E is a field, E over F is a field extension, which means E is an extension field of F. It should not be confused with the quotient vector space. So of course, E is a vector space over F, F is a sub-vector space, and I can talk about E over F as a vector space, but here, in this context, we mean it's just a symbol, and it means that it's a field extension. It's a pair of fields, and E is an extension field of F. It's simply just a notation to be used in compact. This way we can formulate our statements in a compact way. It is also important because we can think about this field extension as an object, and when we talk about what are the symmetries of this object, we mean that we are looking for F automorphisms of E. That's another way to justify this notation. Okay, so that's a field extension, that's finite field extension. Now, what is an algebraic field extension? A field extension, E over F, is called an algebraic field extension if every element of the extended field is algebraic over the base field. So as you can see, in a field extension E over F, I refer to the smaller one as the base field. So we call a field extension an algebraic field extension if every alpha inside E is algebraic over the base field. And let me quickly recall what does algebraic mean. It means that alpha is a zero of a polynomial with coefficients inside the base field. Of course, a non-zero polynomial. And what we showed was that if I tell you a field extension is a finite field extension, if the dimension of this E as an F vector space is finite, then it is an algebraic field extension. So every finite field extension is an algebraic field extension. If a finite field extension can be generated by finitely many elements, then it is also, if an algebraic field extension is generated by finitely many elements, then it is also a finite field extension, but the converse in general is not true. Then another important concept that we introduced was normal field extension. So what is a normal field extension? A field extension E over F is called a normal field extension if for every element alpha, first of all, it should be algebraic, and every alpha that I give you in the larger field, when I consider the minimal polynomial of alpha over the base field, then this polynomial should be split, should be factored into linear factors over E. Alternatively, I can say that the minimal polynomial of alpha over F contains all of its zeros inside E. If this is the case, then we say that this is a normal field extension. So again, if I manage to write down minimal polynomial of every alpha inside E as a product of linear factors inside E bracket X, then it is called a normal field extension. Now, another concept that we introduced close to the end of the previous quarter was a separable field extension. What is a separable field extension? A field extension, E over F, is called a separable field extension if, again, in this course, we assume that it's an algebraic extension. This concept of separability can be defined for extensions that are not algebraic, but that is more subtle, and we are not going to deal with it in this course. In this course, we deal with algebraic field extensions, and we say this algebraic field extension is separable if every minimal polynomial of some element inside the larger field over the base field does not have multiple zeros in its splitting field. So every minimal polynomial is a separable polynomial. So that was the definition of separable polynomial. A polynomial is called a separable polynomial if all of its irreducible factors do not have multiple zeros in their splitting fields. So if they do not have multiple zeros in their splitting fields, then we call them we call this field extension a separable field extension. It is also useful to point out that we had proved a polynomial f does not have multiple zeros in its splitting field, if and only if it is coprime with its derivative. We will come back to this important criterion later in order to understand separable extensions better. But for now, I want to remind you some of these concepts that we have discussed in the previous quarter. Now, let me quickly go over some of the important theorems that we have proved about these concepts. So, for instance, the next theorem that I'm going to recall tells us two other important properties of finite normal extensions. So, in fact, we showed that a field extension, a finite field extension, is a normal extension. A finite field extension is a normal extension if and only if the other properties hold. So in fact, for a finite field extension, these properties are equivalent. So what are the properties? The first property is a constructive property. What do I mean by that? E is a splitting field of some polynomial. If this is the case, so this is the first property that's going to be equivalent for this field extension to be a normal extension. So E is a splitting field of some polynomial. E is generated by zeros of some polynomial over the base field, capital F. Now, the second property is about the symmetries of field extensions on top of E. So, and how they act on E. So what is the statement? If I give you any field extension of E, if I take an F linear automorphism, an F isomorphism of L to L, then it's going to leave E invariant. It's going to send E to itself. So if I, for any field extension of E, so I'm going beyond the field extension that I'm given in order to gain information about the field extension E over F, I can go on top of that and then send L to itself via some theta. And then what I'm saying is that definitely this theta is going to send E to itself. So this is send to itself. So that's the second property. It's equivalent to saying that E is a splitting field of some polynomial over the base field, capital F. And this property is also equivalent to saying that this field, the field extension E over F, is a normal extension. The normal extension is completely internal. It's about minimal polynomial of elements. And the second property is kind of external. It's about field extensions on top of E and the symmetries of that extension. And the first property is completely constructive. Many examples, it's much easier to deal with the first property in particular examples in order to understand if a given extension is normal or not. So altogether, we get a fairly good understanding of finite normal extensions using this theorem. Okay, so this theorem gives us a good understanding of finite normal extensions. Now, one can use this theorem, especially the second part, and get a fairly good understanding on how the symmetries of normal extensions work under restriction. So what do I mean by that? So suppose that E over F is a normal extension, then any extension L of E that I give you, I can talk about restriction map from F automorphisms of L to F automorphisms of E, and it's going to be a well-defined group homomorphism. So again, notice that because of the second property over here, because of the second property, if theta is an F automorphism of L, when I restrict to E, it is sent to E. So this means restriction of this theta to E indeed gives us an F automorphism of E. So this R sub L comma E is a well-defined map. And it is rather clear that it is a group homomorphism because restriction of composite of two functions is going to be composite of restrictions. So it is indeed a group homomorphism. And what is the kernel of this map? What does it mean that theta belongs to the kernel of this? It means when I restrict theta to E, I have to get identity. That means my map is E linear. It's an E automorphism. So restriction, so the kernel of this map is precisely E automorphisms of L. In particular, we deduce that E automorphisms of L is a normal subgroup of F automorphisms of L. Now you see the connection between the concept of normal field extensions and the concept of normal subgroups. So in fact, the motivation was the other way around. So people wanted to understand normal field extensions, and that's how the concept of normal subgroups come out. Anyway, so now we get this, that when E over F is a normal field extension, then E automorphisms of L form a normal subgroup of F automorphisms of L. Now, the next question that we can ask ourselves is that, okay, now we understand the kernel of this group homomorphism. How about the image of this group homomorphism? And we proved that if L over F is a normal field extension, not over E, but rather over F, is a normal field extension, then this restriction map is surjective. Alternatively, I can say that any F automorphism of E can be extended to an F automorphism of L. So if L over F is a normal extension, then automorphisms of F automorphisms of L surject onto F automorphisms of E, and the kernel of this surjection is precisely the E automorphisms of L. So by the first isomorphism theorem for groups, we deduce that the quotient group of the F automorphisms of L by E automorphisms of L is isomorphic to F automorphisms of E. So it is common to get confused between these groups. One rule of thumb is that when you are working with F automorphisms of L, the only trivial subgroups are, again, they should be consisting of automorphisms of L. So the only possible subgroup is that you have to consider, again, automorphisms of L with a bit more restriction. So not only F linear, but also E linear. So that makes it a subgroup of F linear automorphisms of L. So we get this subgroup, this normal subgroup, as we have pointed out over here. And this quotient is always isomorphic to some subgroup of E automorphisms of F automorphisms of E. But when L is a normal extension of F, we also show that it is surjective. Okay, so let me see. Oops. Okay, so far, these were the things that we proved about normal extensions. I also talked about normal closure, but we'll get back to that later on. Now let's see what we have proved about normal and separable extensions together. And about the splitting fields. In order to combine this normal and separable extensions together, we need to go back to splitting fields and recall a statement about uniqueness of splitting fields, and more than that. What do I mean by uniqueness? Let's start with that. So suppose that I give you two base fields that are isomorphic. So F and F prime, both of them are isomorphic. So these are my base fields. So as you see, I put them in the base. Now I'm going to create a tower on top of this base. So the E guy on top of F is nothing but a splitting field of a polynomial over the base field F. So I have the base field capital F. I am giving you a polynomial small f inside this f bracket x. And then I'm considering the splitting field on top of that. Now, I use my translator theta. I go to the other base f prime, and then I apply theta to my polynomial small f, and I consider the splitting field of theta of f over the base field f prime, and I call that E prime. So E prime is a splitting field of the polynomial theta of f over f prime. Now, when we want to say that these splitting fields are unique up to isomorphism, this means I'm asking for some isomorphism from E to E prime. We are we don't necessarily, we not only look for an isomorphism from E to E prime, but in fact, we look for an isomorphism that's compatible with theta. So what does that mean? So we are looking for some isomorphism from E to E prime that is compatible with theta, which means I'm looking for theta hats that are isomorphisms from E to E prime in a way that when I restrict them to F, I end up getting theta. I can visualize this in this diagram. I'm looking for those theta hats that makes this diagram commutative. It's a commutative diagram. That means it doesn't matter if I first go up from here. So I start with some A over here. I can go to the other base field, theta of A, and then look at it as an element of E prime. Or I can go up here, view A as an element of E, and then go via theta hat. And when we say it's a commutative diagram, it means that we end up getting the same value. So theta hat of A is the same as theta of A, which means that when I restrict theta hat to F, I end up getting the same map as theta. So the set of all these isomorphisms we denote by isom sub theta of E comma E prime. And what we showed as part of uniqueness of splitting fields is that this set is indeed non-empty. We do have isomorphisms from E to E prime that are compatible with theta. Now, this was part of isomorphisms, but then we wanted to, so this is kind of a lower bound. It's non-empty. We always have something inside this. Now we wanted to control from the other side. We wanted to say we don't have many of them. We showed that the number of such isomorphisms can never be more than the degree of this field extension, which means the dimension of E as a vector space over F. And moreover, when the polynomial F is separable, in the separable case, equality holds. And this was the key result that helped us to understand normal separable extensions. So when my polynomial small f is a separable polynomial, again, that means all irreducible factors of this polynomial do not have multiple zeros in their splitting fields, and therefore do not have multiple zeros in E. So in that case, we say this polynomial f is separable. So when the polynomial f is separable, then the number of theta isomorphisms from E to E prime is precisely equal to the degree of this field extension. So in the separable case, we have the equality. In general, we have an upper bound. Always we have uniqueness. That means that always we know that this set is non-empty. This was a major result that we proved by a strong induction, and this helped us to show the following theorem, and this was the last theorem that we proved in the previous quarter, that if I tell you E over F is a finite field extension, then the following properties are equivalent. What are the properties? First, E is a splitting field of a separable polynomial. Over the base field, capital F. The number of F automorphisms of E is precisely equal to the degree of the field extension. The field extension E over F is a normal separable field extension. So why 1 implies 2 is immediately a consequence of the third part of this more general statement over here. When I apply this result for theta equals to identity map, F equals to F prime and theta identity immediately implies that 1 gives us 2. Then why 2 implies 3 was more subtle. Again, we used this previous result, but we had to use the ideas of the proof as well, not just the statement. And why 3 implies 1 was an argument similar to what we had over here when we wanted to show that, and being a normal extension implies that the extension is a splitting field of some polynomial. We went almost a normal finite normal extension. We went through that argument and then checked that the polynomial that we end up getting is indeed separable because of the separability condition. So these were the major results that we proved, and this last theorem brought us the definition of Galva extension. An algebraic extension E over F is called a Galva extension if it is normal and separable. So a normal separable extension is called a Galva extension. And this theorem that we proved over here shows that a finite Galva extension is so a finite extension is a Galva extension precisely when it's a splitting field of a separable polynomial, And this is the case precisely when the number of F automorphisms of E is equal to the degree of the field extension. Okay, so now let's try to get a better understanding of Galva extensions, see how we can navigate within the subfields of the Galva extension, if we can understand the symmetries of field extension better, and so on. So again, the list of questions that we are going to consider and try to address are the following. How much symmetries of a field extension can tell us about the field extension? So this concept of how much information we can gain by knowing about the symmetries of an object, it's an important technique in mathematics. It kind of goes to the so-called Klein's program to understand different geometries, where he asked how much symmetries of a geometry can tell us about the geometry. So projective geometry, of course, Euclidean geometry, projective geometry, affine geometry, and so on. So the same concept is here as well. We want to understand how much symmetries of a field extension can tell us about the structure of the field extension. So that's one of the questions that we want to understand, more or less. The other question is how much actually we can compute or understand the group structure of symmetries of a field extension. So what can we say about the group structure of automorphisms, F automorphisms of E? And what is the connection between these two questions? For instance, is it possible to understand intermediate subfields of a field extension if I tell you the symmetries of this field extension? So what are the possible intermediate subfields of a field extension? So these are the questions that we want to understand better. And to that end, we start with the group of symmetries, the automorphisms of F automorphisms of E. So going back to group theory, a general comment is that the best way of understanding a group is letting it act. So I often say that you cannot understand a person better, and you cannot understand a person at all if you don't look at the action of that person. So the same is true for groups. You have to let it act, and then that way you get a better understanding of the group. So, and the group of symmetries of any object naturally acts on that object. In particular, the F automorphism of E acts on E. So what does that mean? So for every F automorphism theta of E and alpha inside E, theta acts on alpha, and that means I'm looking at theta of alpha. I get another element inside the field E. This defines a group action. Let me quickly recall basics of group actions. You've seen this in your group theory course, but let's quickly recall what it is. We say a group G acts on a set X when we have a binary operation. It takes a pair of elements, one inside the group G and one inside the set X. And when I let it act, and I look at the dot G dot X, I end up getting another element inside the set X. So given the pair G comma X, I look at G dot X and I get another element inside the set, capital X. Now, what kind of properties are we looking for? The identity of the group dot X should send it to itself. That should be true for every element of the group. So identity of the group G acts as the identity map on the set X. And G1 dot G2 dot X, it should be the same as G1 times G2 inside the group dot X. This should be true for every G1, G2 inside the group, and every element X. So the best way of thinking about it is by saying that I'm thinking about G as kind of symmetries of the set X, and I'm letting that let it act on the set X. In group theory, you've seen that two important concepts related to group action are orbits of points. Essentially, this means under this group action G, what points look the same as the point X, small x. So the G orbit, the G orbit of X is the set of all the points that look like the same as X if I let the group G act on it. So essentially, if I think about G as the group of symmetries of my object, I'm asking what points look like the same as X up to symmetries. So that's called the orbit of the point X. And the other thing is the stabilizer subgroups of G. The stabilizer subgroup of G with respect to the point X is the set of elements inside the group that fix the point X. So that's called the stabilizer, stabilizes X. The stabilizer subgroup of G with respect to X. This is a subgroup of G, and the importance in the connection between the G orbit of X and the stabilizer subgroup of G with respect to X is given in the orbit stabilizer theorem. So the orbit stabilizer theorem says that there is a bijection between the cosets, between the left cosets of the stabilizer subgroup with respect to X and the orbit of the G orbit of X. And what is the bijection? We send the coset represented by the element G to where G sends X. So the coset represented by G is sent it to G dot X, and this is a bijection. In particular, if these sets are finite, in particular when the group G is finite, let's say, then the number of elements inside the G orbit of X is the same as the index of the stabilizer subgroup with respect to X inside G. Okay, this is the orbit stabilizer theorem. And I wanted to quickly recall the orbit stabilizer theorem, the importance of understanding the G orbits and the stabilizer subgroup. So whenever you have a group action, it's a good question to ask. What can I say about the stabilizer subgroups? What can I say about the orbits? Okay, now let's go back to the action that we had, meaning I'm looking at the symmetries of a field extension E over F, which means F automorphisms of E, and I'm going to let it act on the set E. So I ask myself, what can I say about a single orbit? And then I ask myself, what can I say about the stabilizer of that thing, and so on. Okay, let's start with actually checking why it's a group action. So the identity map, definitely the way that I'm asking to let it act, I mean, it means I'm applying this map to alpha, and identity doesn't, it sends it to itself by definition, doesn't change it. And when I give you two automorphisms, then theta2 dot alpha, which means theta2 applied to alpha. Then when I apply theta1 to this element, this means theta1 applied to theta2 alpha. It is the composite of theta1 and theta2, and that's exactly how this element acts on alpha. So it is indeed a group action, and this is quite general. This is true for symmetries of any object. So it doesn't have to be a field extension. It's about symmetries of any object. So that group of symmetries acts naturally on that object. Now, in this context now, when I give you an algebraic extension, We have also studied what the orbits are, kind of, at least one direction. So if I tell you E over F is an algebraic extension, and I give you an element inside this field E, then the orbit of alpha under the symmetries, so O sub alpha, the orbit of alpha, the orbit of alpha under the action of the F automorphisms of E is a subset of all the zeros of the minimal polynomial of alpha in E. So this means that these orbits, all of them are finite orbits. Orbit of alpha cannot have more than the degree of the minimal polynomial elements. Alpha is going to be sent to another zero of the minimal polynomial of alpha over the base field, capital F. And stabilizer subgroup of alpha, stabilizer subgroup of the group F automorphisms of E with respect to alpha is precisely those automorphisms of the field E that restricted to F bracket alpha is identity. So they are F bracket alpha linear automorphisms from E to E. In particular, if I use the orbital stabilizer theorem, I deduce that the cardinality of the orbit of alpha is the same as the index of this group, the group of F bracket alpha linear maps, linear automorphisms of E inside the F linear automorphisms of E. So this index inside this group is the same as the number of orbits, number of elements inside the orbit of alpha under F automorphisms of E. We have seen this before, but let's go through the argument because it is important. It tells us how the F automorphisms of E act on this on E. So if I denote the minimal polynomial of alpha by x to the n plus a sub n minus 1 x to power n minus 1 plus dot 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 a sub 0, meaning coefficient of x to the I is denoted by a sub I, and I'm assuming that the degree of this minimal polynomial is n, then by definition that means that when I plug in alpha into this polynomial, I'm getting 0. So alpha to the n plus a sub n minus 1 alpha to power n minus 1 dot 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 a sub 0. This is 0. Now I apply theta, my F automorphism, to this. Because theta is a ring homomorphism, 0 is sent to 0. So 0 is the same as theta applied to this element. Theta is F linear and ring homomorphism. So I'm going to get that this is the same as theta of alpha raised to power n plus a sub n minus 1. You see, it is F linear. So I have to apply theta to powers of alpha and then look at the a sub i's linear combination of those. And it is also a ring homomorphism. So theta of alpha to power I is the same as theta of alpha raised to power I. So altogether, I get that it's the same as this evaluating the minimal polynomial, this time at theta of alpha instead of evaluating it at alpha. So we deduce that theta of alpha is also a 0 of this polynomial. So theta of alpha is a 0 of this polynomial, and that's exactly what we wanted to show. This implies that the orbit of alpha under this group action consists of zeros of the minimal polynomial. Notice that I'm not claiming that all the zeros are here. In some examples, we do not have many automorphisms, and in that case, we cannot get all the zeros. But here, what I'm claiming is that it's definitely a subset of all the zeros of the minimal polynomial. In particular, it's a finite set. So all the orbits are finite. It's important. It gives us an insight on this action. And the other thing that we notice is that theta if theta is in the stabilizer subgroup of the F automorphisms of E, then with respect to alpha, what does that mean? This means theta of alpha is identity. Theta of alpha is alpha, and that implies, because we already know theta restriction to F is F, it's identity of F. We get that theta restriction of theta to F bracket alpha is the identity map from F bracket alpha to itself, and that was the definition of being inside the automorphisms of E that are F bracket alpha linear, or F bracket alpha automorphisms of E. So altogether, we get a good understanding of the stabilizer subgroup of this group action with respect to the element alpha. So by the orbit stabilizer theorem, we deduce immediately this result as well. Okay, so now let's go to this question. So we have already showed that the number of elements inside this orbit is definitely less than or equal to the degree of the minimal polynomial. But now the question is, when do I have equality? When can we say the number of elements of on the orbit of alpha under the group action by the symmetries of this field extension is precisely the degree of the minimal polynomial of alpha over the base field capital F? So the next theorem gives us a concrete understanding of this question. So suppose that I give you a finite field extension, E over F. So E over F is a finite field extension. Then this field extension is a Galva extension if and only if, precisely when, if and only if precisely when the equality holds. For every alpha inside this, the number of elements inside the orbit of alpha under the action of the F automorphisms of E is precisely the degree of the minimal polynomial of alpha over the base field F. In particular, we show, we can deduce it from this statement, but we can also show, within the proof we'll show it, that if E over F is a finite Galva extension, then the minimal polynomial is nothing but the product of these degree 1 factors as alpha prime ranges over the elements of the orbit of alpha. So the minimal polynomial of alpha over the base field capital F is precisely product of x minus alpha primes as alpha prime ranges inside the orbit of alpha with respect to the group action, with respect to the group of the symmetries of this field extension. So again, let's try to understand the statement. So in the previous lemma, we showed that when I let the F automorphisms of E act on E, and I ask myself, where does alpha go? We showed that it's going to go to some zero of the minimal polynomial of alpha. Then we ask ourselves, can we get all of those zeros, and do we get precisely the same number as the degree of the field the degree of the minimal polynomial? The answer is that this equality occurs precisely when the field extension is a Galva extension. So in particular, all the zeros should be inside the orbit, and in that case, I'm going to deduce that the minimal polynomial is equal to x minus alpha primes as alpha prime ranges inside the orbit of alpha. Okay, that's the statement that we want to show. Let's assume that my extension is a Galva extension and try to deduce that every orbit has precisely the degree of the minimal polynomial many elements. Okay, so let's assume that my extension is a normal extension. So it's a Galva extension. In particular, it's a normal extension. By definition, a Galva extension is a normal separable extension. I'm starting with a normal extension. Why am I doing that? Because what am I getting to? I want to understand how many elements I have in the orbit of alpha. We have already discussed that every element inside the orbit is one of the zeros of the minimal polynomial. Now I want to say that every zero of the minimal polynomial can be realized as an element inside the orbit. That's my goal. So I want to start with the minimal polynomial and then split it into linear factors. How can I do it? I can do it when my extension is a normal extension. So because E over F is a normal extension, I can split the minimal polynomial of alpha over F over the base field as product of linear factors over E. So I can find alpha i's inside E such that this equality holds. Now, because alpha and alpha sub i's, both of them, are zeros of the minimal polynomial of alpha over F, and that's an irreducible polynomial in F bracket X, we get an F isomorphism from F bracket alpha to F bracket alpha sub I. This is a result that we proved again. This was a kind of an intermediate step for us to prove this result. Again, let me go back to what we have over here. Yeah, so when we wanted to show this isomorphism result as part of uniqueness of a splitting fields, the stepping stone was this, that we wanted to add 1 0 at a time, and we showed that when we add 0 of an irreducible polynomial, and then we can extend this isomorphism of the base fields to after adding zeros of this irreducible polynomial to the base fields. And then we added zeros one after another to show that we can always find some isomorphism between E and E prime that's compatible with theta. So this was the stepping stone for that proof, that because alpha and alpha I, both of them, alpha sub I, both of them are zeros of an irreducible polynomial, then after adding them to F, I can get an F isomorphism from F bracket alpha to F bracket alpha sub I. Now I want to use that extension result about splitting fields. And I'm going to apply that to the field F bracket alpha 1, alpha 2, alpha n. This is a splitting field of the minimal polynomial. This is a splitting field of the minimal polynomial over the base field capital F, because it's generated by the zeros and it contains all the zeros. So it's a splitting field of the minimal polynomial over the base field F. So again, let's look at this bottom part of this diagram. We started with identity map from the base field F to itself. We used this stepping stone and extended this identity to get to an isomorphism from F bracket alpha to F bracket alpha sub i's. Now, when I add all the zeros of the minimal polynomial, I'm getting a splitting field of the minimal polynomial, not F, but rather splitting field of the minimal polynomial. So do we have an F over here? We don't have an F. Yeah, so F, by F here, I mean the minimal polynomial of alpha. Now, when I apply theta sub I to this, theta sub I doesn't change the coefficients because the coefficients belong to the base field capital F. So I'm getting the same polynomial. So it can be viewed also as a splitting field of theta sub I of F. Now I can use the result that we have. Whenever I give you theta sub I, an isomorphism between this new extended base field, this can be extended to a splitting field. So I can find theta sub I hat. That's an theta sub extension of theta sub I. So I'm going one level above. So the base field was F, then we added 1, 0 F bracket alpha. Now I'm going one step further, and I'm adding all the zeros at the same time this time, and using the result that every isomorphism of the base fields can be extended to an isomorphism of the splitting fields. So altogether, I'm getting theta sub I hat and F automorphism of the base of the splitting field F bracket alpha 1 alpha n. Because the restriction of this to F bracket alpha is supposed to be theta sub I, we get that theta sub I hat sends alpha to alpha sub I. So I'm sending alpha to alpha sub I. I'm deducing that alpha sub I, this other zero of this minimal polynomial, is in this, not quite the orbit, because I haven't extended this, but it is in the orbit of automorphisms of F bracket alpha 1 alpha n. But I want to show that it is in the orbit of automorphisms of E. So I need to extend theta sub I hat to an automorphism of E. How do I know that I can do that? It goes back to this property of normal extensions. E over F, okay, so here we have this, that if I give you a normal extension over here, if this is a normal extension, so it's actually this part, not, yeah, so this surjectivity result that we have over here, this part. Let's try to understand this surjectivity result in a diagrammatic picture. So if I give you E, F, this is identity, this is any map, let's call it hat, theta hat. Then I have L over here, L over here. Assuming that this L over F is normal, then this surjectivity means that I can find theta tilde, that's an isomorphism from L to L that's compatible with these. Now I'm going to use this result over here. So you see, let's try to understand it in this picture. You see, I'm going one step at a time, one layer at a time. We started with identity, then we added 1, 0, we got theta I. Then we added all the zeros, we got the splitting field, we went to theta I hat. Now, because it's a splitting field, it's a normal extension over F. E over F is also a normal extension. We showed that whenever I have tower of normal extensions, we can extend from this lower level to the higher level. As long as the higher level is also a normal extension, we can extend an automorphism in the lower level to an automorphism in the higher level. And because E over F is normal, F bracket alpha 1 alpha n over F is also normal. It's a splitting field, and therefore it's a normal extension. Therefore, we can extend an automorphism of this intermediate field to an automorphism of the larger field. The normal extension comes in handy and help us to extend our automorphism to this larger field. So again, because E over F is a normal extension, and F bracket alpha 1 alpha n over F is also a normal extension, I am allowed and I can extend my theta y hat to theta I tilde and get an automorphism, an F automorphism of E, that's an extension of theta I hat. In particular, this theta I tilde, because it's an extension of theta I hat, still sends alpha to alpha sub I. So this theta I tilde that we managed to find, so we managed to find theta I tilde in the set of F automorphisms of E that sends alpha to alpha sub I. In particular, we deduce that all the elements, all the zeros of the minimal polynomial are indeed part of the orbit of alpha, because we managed to find these automorphisms that send alpha to these elements. We have already proved that the orbit of alpha is always a subset of the zeros of the minimal polynomial. So altogether we get equality, that the orbit of alpha is precisely the set of all the zeros of the minimal polynomial. Now, if I want to understand the cardinality of the orbit, I need to understand if there are multiple zeros or not. Now the separability condition kicks in. Because E over F is a separable extension, the minimal polynomial of alpha over the base field, capital F, does not have multiple zeros. This means all these alpha i's are distinct. And so, altogether we deduce that the number of elements inside the orbit of alpha is equal to n is equal to the degree of the minimal polynomial of alpha over the base field. So this completes proof of this direction. So if E over F is a Galva is a finite Galva extension, then the orbit of every element is precisely equal to the degree of the minimal polynomial of that element. Now we want to go the other way around. So suppose orbit of alpha consists of alpha 1, alpha 2, alpha n, and we want to show, inspired by the first part, we want to show that what happened to my picture? So inspired by the first part, we want to show that the orbit of alpha, we want to show that the minimal polynomial of alpha over the base field F is equal to the product of the degree 1 factors x minus alpha i's. In order to show this equality, let's start with the observation that every element of the orbit is a zero of the minimal polynomial. I think I need to stop my video and then I'll come back because the quality is low. Sorry for the interruption. Now, okay, so where were we? Now we want to start with the understanding of the orbit, at least the cardinality of the orbit, and we want to show that the extension U over F is a Galva extension. Now, suppose the orbit of alpha consists of the elements alpha 1 alpha n. Inspired by the first part, we want to show that the minimal polynomial of alpha over F is precisely product of the linear factors x minus alpha i's. Okay, what do we know about alpha i's? We know that they belong to the orbit of alpha, and therefore they are indeed zeros of the minimal polynomial of alpha over F. that we proved in the previous lemma. Therefore, by the generalized factor theorem, and here I'm assuming that alphas are distinct, these are distinct elements of the orbit. So by the generalized factor theorem, I can find some polynomial Q and write down the minimal polynomial as product of these linear factors times this factor Q. Now, if I compare the degrees of both sides, by assumption n is supposed to be the degree of the minimal polynomial, that means the degree of this extra factor Q should be 0. And now if I compare the leading coefficients, minimal polynomial is a monic polynomial, x minus alpha i's are monic. We deduce that the leading coefficient of Q should be also 1. It's a degree 0 polynomial with leading coefficient 1, so it's just 1. So by assuming by the hypothesis that the degree of the minimal polynomial is precisely the number of elements inside the orbit, comparing degrees and leading coefficients, we deduce that Q is just 1, and that means the minimal polynomial is nothing but the product of these linear factors, x minus alpha i's. Now, what do we deduce out of this? First of all the zeros of the minimal polynomial are inside E. And that's true for every alpha inside E, which means E over F is a normal extension. That's the definition of being a normal extension. Second, all the zeros of the minimal polynomial of alpha over F inside the splitting field, inside this E, are distinct. And therefore, all the minimal polynomials of the all the zeros of the minimal polynomial of alpha over the base field F in their splitting field, in its splitting field, are distinct. And that means that this extension is a separable extension. So we showed that E over F is both normal and separable. And that's a definition of being a Galva extension. So E over F is a Galva extension. So we showed that a finite field extension E over F is a Galva extension if and only if the cardinality of every F automorphism, every orbit of alpha, every orbit of the elements inside E under the group action of the symmetries of this field extension is precisely the degree of the minimal polynomial. So understanding the cardinality of the orbits give us a very good understanding of the field extension. So that's the concept that you should take out of this theorem, and of course, precise formulation. Again, every orbit has precisely the cardinality. Every orbit of alpha has precisely the degree of the minimal polynomial of alpha many elements. So that's equivalent to saying that the field extension is a Galva extension. Now, we want to give an understanding between subgroups of the group of symmetries and subfields or intermediate fields of this field extension. And this connection is given via understanding the fixed points of this subgroup. Let's go into the definition. So suppose G is a subgroup of the group of symmetries of this field extension. Then the set of fixed points of G, let's denote it by this fixed parenthesis G. This by definition means all the elements of E that are fixed by all the elements of the group G. This fixed G is going to be an intermediate subfield. Okay, let's see why this is the case. The proof is rather easy, but let's quickly go through the proof. So first of all, why do we have this set inclusions as sets? So for every F automorphism of E, by definition, alpha of, for every alpha inside F, theta of alpha is alpha. That's the definition of being an F automorphism. So F is a subset of the set of fixed points of G. Now, the fact that fixed G is a subset of E is clear because I'm only considering elements inside E anyway. So we have that fixed G is a subset of E and it contains F. So as sets, we are set. Now let's see why it is a subfield. Why do we have the field structure and this guy? I pick two elements inside this set. Now I pick an element theta. I have to argue why alpha minus beta is also fixed by theta. But theta of alpha minus beta is theta of alpha minus theta of beta, because theta is a ring homomorphism. And alpha and beta, both of them are fixed by elements of G. Therefore, theta of alpha is alpha and theta of beta is beta. So altogether, you get that alpha minus beta is also fixed by elements of G. Similarly, theta of alpha times beta is theta of alpha times theta of beta. Alpha and beta are fixed by theta. Therefore, it is alpha times beta. So altogether, we get that alpha times beta is also fixed by all the elements of the group G. So alpha minus beta and alpha times beta belong to the fixed points of the group G. Now, why do we have the inverses? So if alpha is inside fixed points of G and it's not 0, then because E is a field, it is invertible inside the field E. Now, theta is an automorphism of this field. So theta of alpha inverse is theta of alpha inverse. So it is equal to, because alpha is fixed under all the elements of the group G, theta of alpha is alpha, and therefore theta of alpha inverse is alpha inverse, which means alpha inverse is also among the fixed points of the group G. Altogether, we get that fixed points of G is a subfield, is an intermediate field. Now, this gives us a very good understanding. This gives us a connection between Galva extensions and the fixed points of a group. This next theorem helps us to get this connection. So suppose that E over F is some field extension. And suppose that G is a finite subgroup of F automorphisms of E. Let's call the set of fixed points of this group K. Then my claim is that the extension E over K, E over the fixed points of this group, is in fact a Galva extension. In fact, we get a bit more. We get that the minimal polynomial of alpha is product of x minus alpha primes as alpha prime ranges over the orbit of alpha, the G orbit of alpha. So G dot alpha means the G orbit of alpha. So this notation means this is the G orbit of alpha. That's a G orbit of alpha. So what I'm saying is that I don't need to go to the full K automorphisms of E and look at the orbit of alpha on that map. I can only consider the G orbit of alpha, and that's enough for me to get the full minimal polynomial. That's part of this result that we are going to show. And the second part is that E over K itself, E over the fixed points of this group action is a Galva extension. Okay, let's go through the proof. I'm going to prove both parts at the same time. Let's start with the polynomial that we were interested in, which means the product of x minus alpha primes as alpha prime ranges over the G orbit of alpha. And let's call that guy to be f sub alpha comma G. So I'm starting with the group G. I'm looking at the G orbit of alpha, and I look at all the linear factors x minus alpha prime as alpha prime ranges over this G orbit of alpha. I look at the product, I call it f sub alpha comma G. My claim is that this is precisely the minimal polynomial of alpha over the base field capital K. But in particular, I need to show that this polynomial does belong to K bracket X. Let's start with that. What does K bracket X mean? It means I need to show that all the coefficients of this polynomial are fixed by elements of the group G. So I pick an element inside the group G and let it act on this polynomial. So I pick alpha and I let it act on the polynomial f sub alpha comma G. So how does an element inside the group act on this polynomial? So this essentially means that elements of G are automorphisms of the field E. So I let them act on the coefficients of these polynomials. But this action is also a ring homomorphism, so I can alternatively let it act on these linear factors. So theta doesn't change x, x goes to x, but it does send alpha prime to theta of alpha prime. So as alpha prime ranges inside the G orbit of alpha, I ask myself, what does theta do to this orbit? So alpha prime is ranging in the G orbit. Then I apply theta to this G orbit, and I ask myself, where does the G orbit go? So I'm looking at I'm picking some element inside the G orbit. That means what? It means that it is theta prime of alpha for some theta prime inside the group. That means that's the definition of being inside the G orbit. Now I'm applying my theta to this guy. So this means theta of alpha prime is theta of theta prime of alpha. I'm looking at the composite of theta and theta prime, which is another element of the group, and let it act on alpha. Now notice, so theta composed with theta prime is another element inside the group. So I'm getting another element inside the G orbit of alpha. And notice that as theta ranges, as theta prime runs over the entire group, theta composed with theta prime also ranges over the entire group. This composition gives me a permutation of the elements of the group. So theta permutes the elements of the orbit of alpha. But alternatively, I can say like this, that theta, by this argument, sends an element of the G orbit of alpha to an element of the G orbit of alpha. I can run the same argument and say theta inverse also sends elements of the G orbit of alpha to elements of the G orbit of alpha, and they are inverse of each other. So altogether I get that theta just permutes elements of the G orbit. So as alpha prime ranges over the G orbit, so does theta of alpha prime. So theta of alpha prime is also ranging over the G orbit in a unique way. So again, what does that mean? This means if I go back over here, as alpha prime ranges over the G orbit, so does theta of alpha prime. So if I call theta of alpha prime to be alpha double prime, then alpha double prime is also ranging over the G orbit of alpha. So altogether, I end up getting that theta, when I apply theta to this polynomial, I'm still multiplying x minus alpha double primes as alpha double prime ranges over the orbit, which means I'm getting back the polynomial f sub alpha comma G. You see, this was the product of these linear factors as alpha double prime. I mean, alpha prime was ranging over the G orbit of alpha. I'm getting the same thing over here. So altogether, what did I end up getting? I showed that f sub alpha comma g is fixed under the action of the elements of the group G. Again, what does that mean? This means all the coefficients of this polynomial are fixed by all the elements of the group G. So they belong to the fixed points to the group G. You see, they belong to the fixed G. So this means this polynomial, all the coefficients belong to the fixed points of the group G. It is inside K bracket X. We also notice that by definition, alpha itself belongs to the orbit of alpha because identity is inside the group. So alpha does belong to the G orbit of alpha. And so alpha is a zero of this minimal polynomial. I mean, alpha is a zero of this polynomial. So altogether, what did I end up getting? I get a polynomial in K bracket X, which has alpha as a zero. That means the minimal polynomial of alpha over K should divide this polynomial. In particular, the degree of the minimal polynomial cannot be more than the degree of this polynomial. This polynomial was the product of the elements inside the G orbit of alpha. So the degree of this polynomial is precisely the cardinality of the G orbit of alpha. Okay, so far so good. But on the other hand, this G is a subgroup. This G is a subgroup of the K automorphisms of E. Again, notice, so let me write it down here. So K is the set of fixed points of G. That means G can be viewed as a subgroup of K automorphisms of E. So that means the orbit of alpha under this larger group can only get larger. On the other hand, every element inside this orbit is still a zero of the minimal polynomial of alpha over K inside this field D. So we get that the number of zeros of this, which has an upper bound, that's the minimal polynomial of alpha over K. Okay, now I can combine these two results, which results again, the degree of the minimal polynomial of alpha over K cannot be more than the cardinality of the orbit of alpha under the group G. But on the other hand, the number of elements of the orbit of alpha under this possibly larger group, the K automorphisms of E, cannot be more than the degree of the minimal polynomial of alpha over K. Now, if I combine these two, I get, okay, what do I get? The number of elements inside this orbit cannot be more than the degree of the minimal polynomial. This cannot be more than the degree of the the degree of the polynomial f, because we showed f is inside K bracket X and it does have alpha as a zero. And then this means, and by the first part, we deduce that it cannot be more than the number of elements inside the G orbit of alpha. And because G is a subgroup of this, we automatically get this upper bound. That means all of these terms should be equal. All of them are the same numbers. In particular, we get that the degree of the minimal polynomial of alpha over K is the same as the degree of the polynomial f, and it's the same as the number of elements inside the orbit of alpha. By the previous theorem, we deduced that this field extension should be a Galva extension. So K is a Galva extension. And moreover, because the degrees of these two polynomials are equal and the minimal polynomial divides the other one, they have the same degree, we deduce equality, and that gives us the moreover part. So altogether we get all the parts that were needed. In particular, we get that E over the fixed points of a subgroup is always a Galva extension. So we'll continue and try to understand what is precisely the degree of this field extension in the next lecture. For now.